Here's another example of a problem very similar to what we just did. And in this problem, we're also going to use the grams to moles to moles to grams dance thing. Sorry, your instructor has a strange sense of humor. But anyway, let's say that we're going to take 1 pound, which is 454 grams. And I didn't even put up pounds there because we don't want to use American units if we don't have to, basically. But anyway, 454 grams of ammonium nitrate. And we're going to decompose it. And the question is how much N2O, dinitrogen monoxide, and water, H2O, will be formed. And also you can see there I tacked on what is the theoretical yield of the products, which we'll talk about here in a little bit. Okay, well, before you start a problem like that, you've got to have a balanced reaction. And at this point, we know that NH4NO3 is going to be the reactant, and it's going to break down to N2O and H2O. So when you look at those long enough and you balance it, you'll see that there's going to need to be a 2 in front of the hydrogen. NH4NO3 has 2 nitrogens, 4 hydrogens, and 3 oxygens. And you can see on the product side there that with a 2 in front of the water, you have 4 hydrogens, there's 2 oxygens in water, and another oxygen and N2O for 3 oxygens, and N2O has 2 nitrogens. So that's the balanced reaction. Very, very important. The next thing we're going to do, we have to turn the grams of reactant, ammonium nitrate, into grams of product. This is going to be grams, moles, moles, grams. Now you've got 2 choices here. You could do water or N2O, and it honestly doesn't matter. In this example, I'm going to do water first. So what we're going to do, we're going to turn grams of ammonium nitrate into moles of ammonium nitrate using the molar mass. We're then going to use the balanced reaction to have 1 mole NH4NO3 to 2 moles water. So what that's going to look like, 2 moles of water on the top, 1 mole NH4NO3 on the bottom, and that'll allow us to go from moles of reactant into moles of product water. Then we can take the moles of water, turn it into grams of water using the molar mass of water. Pretty chill. So here's what this looks like, all right? What this is going to look like, we're going to start on the left there, 454 grams of ammonium nitrate. And when you figure out the molar mass of ammonium nitrate, it's about 80.04 grams per mole. And check this out. Make sure you can do this. This is a Chem 221 thing, but I don't want that to stop you here in Chem 222, so make sure you're good. That'll allow us to go grams of reactant into moles of product, moles of ammonium nitrate. Now this next part, the 2-to-1 ratio, it's not magic. 2 moles of water, which is what we're after in this particular part of the problem, to 1 mole ammonium nitrate. So we're using a 2-to-1 ratio here to turn moles of reactant into moles of product. Then we'll multiply by the molar mass of water, which is about 18 grams per mole, 18.02 grams per mole. So after we canceled the grams ammonium nitrate, we're going to cancel the moles of the ammonium nitrate. We then got moles of water. Moles of water cancel to get grams of water. 204 grams of water should be produced by that 454 grams of reactant. 204 grams is called the theoretical yield because that's how much we should be able to make. And we'll talk about why that's important here coming up. But if all goes perfectly well and we don't spill any chemicals or contaminate it, or I don't drop my coffee in there or something like that, we should be able to get 204 grams of water from our 454 grams of ammonium nitrate. There's another product, though, in this problem, dinitrogen monoxide, N2O. And to figure out how many grams of dinitrogen monoxide you could get out, you could do the grams, moles, moles, grams dance one more time. You'd start with the 454 grams ammonium nitrate and turn that into moles, and you've already got the molar mass. The ratio between ammonium nitrate and N2O would be 1-to-1. So you'd have equal moles N2O to moles of NH4NO3, and then you'd multiply by the molar mass of N2O to figure out how many grams there were. But in this particular problem, there's another way to do it, because law of mass action, law of conservation of mass, says all the mass that goes in, i.e. the reactants, equals all the mass that comes out, i.e. the products. So in this problem, 454 grams is how much we put in, and we just calculated that we're going to get 204 grams of water out, and you can see that those those numbers are not equal. So whatever the N2O is going to be, it's going to be equal to 454 minus 204. Total mass in minus grams of water is going to equal N2O. This is an alternate way to figure out the N2O. Now, honestly, I would usually go grams, moles, grams for N2O, and I encourage you to check that out. However, this is an easier way, as you can tell if it works, and we'll talk about that more later. So while 204 grams was the theoretical yield of water, 250 grams is the theoretical yield of N2O. We should be able to make that much N2O using 454 grams of ammonium nitrate. In this problem, the reason I'm kind of hedging my answers and why I say I usually go grams, moles, grams, is that we're using what's called stoichiometric amounts, perfect amounts of reactant and product. There's no excess at the end, left over or something, and it honestly is kind of a rare occasion in chemistry, and I'll show you examples of this here coming up. But anyway, it is an example if you have one reactant, definitely, it's breaking down into a couple products. This way works really well, but there's some times where this method won't work as well, and I'll talk about that more in a little bit. This is a summary of what just happened mathematically, all right? Now, the ammonium nitrate we put in was 454 grams, and although I didn't show the calculation, if you take 454 and divide it by the molar mass, you'll find that you get 5.68 moles of ammonium nitrate, okay? And that's how much we started with. So at the end, we're assuming that all the ammonium nitrate is gone. That's the minus 5.68. But in the process, we end up making 5.68 moles of N2O and twice that moles, 2 times 5.68 moles of water. The ratio of N2O was 1 to 1 ammonium nitrate, but to water, if you remember, it was 2 moles of water for every mole of ammonium nitrate. That's why we multiply it by 2. So at the end, you have 11.4 moles of water, twice as much as the N2O 5.68. And if you multiply those mole amounts by their molar masses, you get 250 and 204 grams. And by the way, that little dot by the 0 shows that it's a significant number. So that's a 3 sig fig value, 250. If you wrote 250 without the dot, it would be like plus or minus 10, 240 to 260 grams. But 250 with a dot would be plus or minus 1, like 249 to 251. That's the sig figs we want. So because the mass that goes in, 454, equals the mass that comes out, 250 plus 204, mass is conserved. And we're not breaking any thermodynamic laws or anything like that. Pat yourself on the back, thumbs up. Pretty cool. This is kind of a general plan for doing these stoichiometric coefficients, and you may find this useful, you may not, but here's the punchline. At the middle, the core of all these problems is going to be the mole-to-mole ratio that comes from the balanced equation. That's the stoichiometric factor, all right? And you may be going reactant to product, product to reactant, reactant to reactant, whatever, but that ratio, that factor, has to come from the balanced equation, and that's why it's so important. Now, what we've been doing so far, we've been taking grams of something, turning it into moles, moles of the thing we started with to moles of what we're looking for, and back to grams again. That's the grams, moles, grams. But you can go even farther from that if you want to. We'll talk about things, ways to go to volume using what's called molarity. We could take the density of the substance and turn the grams into milliliters. You could even use Avogadro's number to turn moles into number of particles using Avogadro's number, 6.022 times 10 to the 23rd. But again, you must have a balanced equation or all of this stuff doesn't make any sense.
Hydrogen peroxide in water decomposes slowly at room temperature. In the presence of manganese dioxide, however, the decomposition occurs much more rapidly. The reaction produces gaseous oxygen and water. The hydrogen peroxide is oxidized and reduced at the same time. It undergoes a disproportionation reaction. The manganese dioxide serves only as a catalyst and is not consumed in the reaction.
If you've ever purchased H2O2 hydrogen peroxide from the store, it always comes in a brown bottle. You're supposed to keep it in the refrigerator, stuff like that. And the reason for it is that H2O2 will decompose. It decomposes into water and oxygen using that reaction right there. And notice the stoichiometric factors, 2 H2O2s make 2 waters and 1 oxygen. That's kind of the idea. Now, if you want to speed this along, you can use what's called a catalyst. We're going to talk more about catalysts this quarter, but a catalyst is a chemical that makes the transformation happen much quicker than it would have been otherwise. A catalyst is something that makes the reaction go faster, but it's not used up itself. And manganese 4 oxide, which this lame video called manganese dioxide, but anyway, manganese 4 oxide is a better name. It will actually break down H2O2 a lot faster than it would have been. So you can see it's pretty exciting when you put MnO2. And the cool part is you could, in theory, just evaporate the water that's left, and you could reuse the MnO2 again. You could have it in another catalyst, stuff like that. But anyway, that's beside the point. I'd like you to try this problem on your own. This is a grams, moles, grams problem that's very similar to what we just did with ammonium nitrate. In this problem, we have 5 grams of H2O2, and I'm curious what mass, grams, of O2 and water you can obtain using this amount. So I'd like you to find the theoretical yields, if you will, of water and O2. How you would start this problem, you'd start with the grams of the H2O2 and turn it into moles of H2O2. Then you have to pick water or O2, doesn't matter. Let's do water first, I guess. That would have a ratio, according to the balanced equation, 2 moles H2O2 on the bottom for every 2 moles of H2O on the top. So that would be how you go from the reactant to the product. And once you have moles of water, you could multiply by the molar mass to get grams of water. When you do the oxygen, you could do the same, start it the same way. Grams, 5 grams of H2O2 to moles using molar mass. You would use 2 moles of H2O2 on the bottom for every 1 mole O2 on the top. That's moles of oxygen, then you multiply by the molar mass of O2 to get the grams of O2. If you did this correctly, here are the answers. So again, try it yourself. You should get 2.35 grams of O2, 2.65 grams of water. So that's the answer you should get. Try it yourself. And if you can't get it, of course, let me know. I want to be able to help you. If you can show me what you're doing, I can try and help you out with different things. Notice how at the end in this problem, if you add those two product amount up, you do get 5.00 grams. All the mass that goes in equals all the mass that comes out. Pretty cool. The theoretical yield is the maximum amount of yield that should be created by a particular reaction. So in the last example there with ammonium nitrate, we calculated the grams of water that should come out and the grams of N2O, stuff like that. But what happens a lot in an actual chemical reaction is that you end up losing some. This reaction has a lot of gases, and it's easy to let like a stop cork or something open up accidentally, and some of the gas escapes. Or maybe there's another chemical around that one of the reactants or products reacts with. So the percent yield is an important concept. Percent yield is nothing more than a ratio between the theoretical yield, which you have to calculate, and the actual yield, which is how much you actually collect at the end of the reaction. And people usually multiply this by 100%. So I have seen chemists trying to create the same chemical but with different mechanisms, like they'll have different reactions. And they will say, well, yes, your method's good, but my percent yield is higher, so my method must be cooler, these kind of things. It's amazing. But anyway, percent yield is a nice way for chemists to compare their reaction pathways and see if there's like a better way to make the particular reaction. So the actual yield should be less. There's 1 or 2 exceptions when it can be higher, but that's never good. Anyway, actual yield is usually less and stuff due to things like not reacting all the way, which is something that happens. Maybe it's a difficult reaction. Maybe, again, you let some out accidentally or spilled some. I mean, these are all legitimate things. Chemists are human, just like everybody else, and all these things can happen. But a percent yield is helpful. Usually, as you do a reaction more times, your percent yield gets better because you're more used to the system. You get better results. So just kind of think about that as we go through these sections. Let's say in the last example, we were supposed to get theoretically 250 grams of N2O. Cool. But for whatever reason, when we did the reaction and we tried to follow the instructions, etc., we only got 131 grams of N2O. All right. That's the actual yield. And again, why we got less, I don't know. You'd have to be in the know of the experiment to figure it out. It doesn't really matter. But we can use this information to calculate the percent yield of N2O. So percent yield is actual over theoretical. So for this problem, that would be 131 divided by 250 grams. Notice they're both 3 sig figs, so we're good to go. Multiply it by 100%. 52.4% yield. So the yield of N2O, 52.4%. And again, it's hard to know what that means. Maybe it's really good, maybe it's really bad. It's easy in academia to think that, well, 90% and higher would be a good yield because that's an A, 80 to 89 would be an okay yield because that's a B, whatever. All right, don't think that way with theoretical yields and percent yields. I once had a percent yield of about 4%. Yes, that's right, 4% of a compound. It was a purple compound, and I was so thrilled. I called my parents. I was in a different time zone at the time. I said, hey, I made the purple stuff. And they're like, it was the middle of the night, right? And they were like, oh, okay, you need to get some sleep now or whatever. But anyway, it doesn't matter. I was the first person who ever made the purple compound. So 4% was pretty cool. All right. Now, as I did it more times, I was able to make that percentage get a lot higher. It never got to 52%. It was very air sensitive and water sensitive. So it was really easy to contaminate. But anyway, regardless, the percent yields, you have to know more about the experiment to know if that's a good yield or a bad yield. Here's another reaction that I'd like you to try yourself and see what you get. This is just a way to test yourself. This stuff is super important to chemists because, again, this is how chemists get paid, remember? So it can be kind of cool. So in this problem, we've got a sample of copper 2 sulfate. We have 1.274 grams of it, and it's reacting with an excess of zinc metal, and we actually get 0.392 grams of copper. So notice that that's the yield that we received. It is not the actual amount that we calculated. So I want you to calculate what the percent yield is going to be here. And there's the equation. So how you would answer that is you take that 1.274 grams of copper 2 sulfate, turn it into moles, use the molar mass. Then for every 1 mole of copper 2 sulfate, you're going to create 1 mole of copper. So in this case, the moles are equal to each other. You can then take that moles of copper, multiply it by the molar mass of copper, 63.546 or whatever. That'll give you the theoretical yield of copper. And I guarantee it's going to be a number less than 0.392 grams. So the percent yield is actual over theoretical. 0.392 grams is what you actually got, divided by the amount of copper that you theoretically calculated, the theoretical yield, times 100%. Good to go. Here's the answers I got. The theoretical yield of copper was 0.5072 grams. And again, I got that from grams copper 2 sulfate to moles copper 2 sulfate, 1-to-1 ratio. So moles copper 2 sulfate equals moles of copper. I then multiplied by 63.546 to get the grams of copper, the theoretical yield. So the percent yield would be the actual 0.392 divided by the theoretical yield 0.5072 times 100, 77.3% copper. And again, try this yourself. Make sure that you're hip with this kind of process.